Welcome to Module 9. So Module 9 is modeling, and it's not like the modeling where you walk down the stage or anything like that. Modeling in math is trying to explain what's going on in nature, and the process of understanding what's going on in nature and explain that using math. That's the process called the modeling. So we do so using graphs and functions and applications. So let's take a look at what the function is. So function is a one-to-one relationship between an input and output. And an input is drawn from what we call the domain. And then the possible outputs are grouped together in the range. And then the function can be represented by a picture, a data table, or an equation. So here's an equation. You throw in some kind of x, the function does its thing, it comes out the output. Or data table like this, and then so in this case the temperature will be called the domain, and then the cocoa sales will be the range. And the domain will be just basically the range between the minimum number and the maximum number of here. And then the range will be the minimum number and then the max number here. So the range is used in a couple different ways, but the domain is the range of these numbers, and the range is the range of these numbers. I know it gets a little confusing, but that's what it is. Using a function, you can represent this using a function like this. If you have taken algebra before, you probably know what this is. Y is equal to 2x plus 3. X in this case is called an independent variable, and then the y is called the dependent variable. It's the x that you can control and manipulate. That's why it's called an independent variable. And then the y is dependent because it depends on the value of x. So for example, up here, the cocoa sales depending on the temperature, whatever the degree is. So this would be considered the independent variable, and this would be considered a dependent variable. Okay. Sometimes this is actually called an equation. It could be expressed as in a function. So if you see f parentheses x, you read it as f of x. So basically you replace the y with f of x. So if you see f of x, this is another way of saying function. Actually, this format right here, it's the form called a linear function, where m stands for the slope and then b stands for the intercept. And this form is called a linear function because if you draw this graph, it's a straight line. And another feature of linear function is that it has a constant rate of change, which is the slope, in this case m. So the problem is a linear function problem. If you see a constant rate of change, or if you graph it, if you have a straight line, then you're dealing with a linear function. Okay. The slope can tell you a couple different things. If the slope is, say, negative, that means the slope is going downward. If the slope is 0, that means it's a horizontal line. And if the slope is positive, that means it's going upward. So you have 3 different types of slope. And wherever the graph intercepts the y-axis, that's called a y-intercept. Okay. There's a slope function. It's this. Slope is equal to changing y over changing x. Or we can use this triangle. It's called the delta. Delta y over delta x. And if you see the slope, that's how you calculate the slope. So let's do an example of finding an equation. And if I ask you to find the equation, what I really mean is, give me this form, and then give me m and then b, and that will complete the linear function. So let's figure out the slope and then the intercept of the graph here. As you can see, the slope is, if you go 1 hour over here, only going up half an inch. So the slope will be changing y, which is 0.5 inches, over 1 inch. So that means 0.5 inch per hour. So that would be a slope. And where's the intercept? Well, it's intercepted here. And what's the y value? At this point, y is 0, so the intercept is 0. So y is equal to 0.5x plus 0, and then we don't write the 0, so then final answer is y is equal to 0.5x. So that would be the equation. Another thing you have to be able to do is extract the equation from word problems. It's really not that hard. Just follow these steps. The steps to take are, first you find the slope. It's the easier of the two, and you cannot find the intercept typically without the slope. So find the slope first, and then find the intercept. And basically plug in those two numbers where the m and then b are and rewrite the equation given the numbers. So here's an example. The average lifespan of American women has been tracked, and the researchers found that in year 1960, the average lifespan was 73 years. Every year since then, the average span has been increasing by 0.2 years. What's the current average lifespan of American women? So the first question is this a linear function problem or non-linear function problem? Well, as you can see, the constant rate of change is 0.2 years. So this is a linear function problem. And so I had to find the slope and then the intercept. Another thing about the intercept is it's typically the initial value, whatever the beginning value is, if it's a word problem. So let's look for these two things, the constant rate of change and whatever the initial value is, and plug that into where the m and the b are. So for the m, it's easy to see because it's the rate of change, which the problem states the average span has been increasing by 0.2 years. So that's my value for m. The slope is 0.2 years. And the initial value, meaning when was the very first time that was tracked? So that was year 1960. And in 1960, the average lifespan was 73 years. So that's my initial value. So that would be my b. So plug in these two, and then I use the t as my variable to represent time. So in this case, y is equal to 0.2t plus 73. So here, let's say in year 2013, the difference between year 2013 and 1960 is 53 years. So they're 53-year span. So that means plug that in 53 where the t is. So 0.2 times 53 plus 73 equals to 83.6. So the final answer is the current average lifespan will be 83.6 years. So not too bad. Just basically find the slope, the initial value, or the intercept, plug it in, then you're done. Another type of function is called exponential functions. And it's really easy to identify an exponential function because you see this exponent, the little number, in this case the t. So if you see something like that, that's an exponential function. It's typically, it grows or decays by the relative amount per unit of time. And q is the end result, and q0 is the initial value. R is the rate, and the t is time. So here's an example. Oh, and if you're asked to graph this, I would do this in Excel, which I'll show it to you in a little bit. But let's take a look at the example first. The population of a popular vacation town of wherever it is in 2013 was estimated to be 35,000 people with an annual rate of increase or growth of about 2.4%. Model this scenario. Make a table showing the first 10 units of time. Make a graph of the exponential function. And calculate what the population is at year 2013. So model this scenario, that means give me the function. So I know this is going to be an exponential function because I see the growth about 2.4% every year. So then Q will be the population at any time t, whatever the time in future. The initial population is 35,000. The rate is 2.4%, so I'm going to convert that to a decimal by divided by 100. So 2.4% equals to 0.024, 0.024, that's it. And t is whatever the time we want. So the model will be, plug it in to here, Q is equal to 35,000 times parentheses 1 plus 0.024 parentheses to the t power. So just add the 1 and 0.024 to be 1.024. So the model is Q is equal to 35,000 times 1.024 raised to the t power. That follows this model right here. So how do we model this using Excel? So let me switch to Excel here. So here's my initial value. So for the second year, I need to calculate what that is. So it's going to be 35,000 times 1.024 raise it to the t, and then that's how you do the raise to the t power. So this little hat thing is shift 6 to the a3 power. That means that's the first year. So type that in and basically drag it down all the way down. So you see that it's the same, except that the t is different. And finally, year 10, 44,368. Okay. So that's how you model this using Excel. Just type in the function, drag it down, you get the final answer. If you get too many decimals, use one of these buttons to get rid of the decimal points. The second set of things you have to do is graph this to see if it's exponential or not. We already know it's exponential, but let's model this, or let's graph this to see what it looks like. So just like before, just select all the data, go to Insert, and I'm going to do a line graph, which is here, a line chart. Okay, I'm going to pick the first one, and it looks like this. It's good, but there's one thing I don't need, is that I don't need to show the year. I just need to show the population. So in that case, just click on the year and then right click and just delete it. It'll get rid of it. And yeah, I see the population. It's a little out of scale, so it's kind of hard to see, but it is curved. So that means this is nonlinear. So this will be a nonlinear function problem. Alrighty. So there's another thing you need to know how to do is exponential. Here's a log problem. What the log does is it's a inverse of exponential function. So when you see something like log of 10 to the x is equal to 4, that means what's the number x that has 4 zeros after 1? That's the question. So this is saying, give me a number x that it has 4 zeros after 1, 10 to the 4th power. So in this case, do 10 to the 4th power, 10,000. That's your answer to this kind of log problem. So that concludes the lesson on modeling.